Polar covalent bonds are bonds that are present when the bonding electrons are attracted more strongly by one atom than by the other. So that just means that the electron distribution is not the same. If we look at a covalent bond between two of the same atoms, they're going to have similar polarities. If you have one that is slightly more electronegative, then the way that your electron density is going to be weighted is slightly more on the electronegative atom versus this one over here. So if you have a difference of electronegativity between two atoms in a bond, the one that is more electronegative is more likely to carry more of the electron density than the other. So this would be a covalent bond where it's shared equally. This is a polar covalent bond where you can draw a dipole arrow. If there's enough of an electron difference, it becomes an ionic bond where the electronegative atom is carrying all of the electron density and this is taking none of that. So the electronegativity is the intrinsic ability of an atom to attract electrons. The differences in electronegativity between two atoms in a bond produces bond polarity. Or fluorine is the most electronegative one, and the trend increases as you move in this direction. So the lowest electronegative atom is cesium at 0.7. And halogens and nitrogen oxygen tend to be more electronegative. So with non-covalent bonds, you have atoms with similar electronegativity. En is abbreviation for electronegativity. CH is an example of two atoms that have non-polar covalent bonds. Polar covalent bonds have a difference in electronegativity of atoms. So the examples of these would be carbon to oxygen, oxygen to hydrogen, or carbon to a halogen. Ionic bonds generally occur between a metal and a nonmetal. So if we look at these two examples here, we have methanol, which is a bond between carbon and oxygen. And the electron density, you can see here from this electron density map, the red indicates that it's negative. This is going to be positive. So we have the dipole arrow here with the electron density on the oxygen and the partial positive on the carbon. Methyl lithium, this is more of an ionic bond between carbon and lithium. You can see this is very blue versus this was a slight green color, and this is very red. So the dipole arrow is drawn in the opposite direction, where carbon now has that negative charge, lithium is positive. What an inductive effect is a shifting of electrons in a bond in response to the electronegativity of nearby atoms, which we can see with this carbon in the methyl lithium. And we'll see more examples of inductive effects later on. All right, so for our practice problem, use the partial positive, partial negative to indicate the direction of expected polarity for each of these. So we have CH3, CH2OH. If you were to draw those out, I have CH3, CH2, and then OH. Oxygen has two lone pairs. Each carbon has 4 bonds. Oxygen has 2 like it should. If I look at the electron density of this one, the carbon is partial positive because it is less electronegative than oxygen, which is one of the electronegative atoms. The dipole arrow is going to move in this direction. So this is the structure of ethanol. So that is a polar compound because there's an uneven distribution of electron density. If we look at CCl4, we have C, Cl, 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 Cl. Chlorine is very electronegative because it's right under fluorine. So I can draw partial positive here, partial negative to each of these chlorines, and dipole arrows to each of these as well. So there are polar bonds here. But because each of these are pulled in different and equal directions, the overall molecule is nonpolar. If we look at the definition of a Bronsted-Lowry acid base, which is often shortened to Bronsted, a Bronsted acid is a substance that donates a hydrogen cation. And the Bronsted base is one that accepts the H+. H+ can also be referred to as a proton. A proton is a synonym for H+. If we look at this reaction here, we have HCl plus HOH, which gives Cl- and H3O+. If we try to figure out what is acid and what is base, we can look at the other half of the reaction. So if we notice here, the H and the Cl on the other side, this is losing the H, which means that this HCl is the one that donated it. The one that donates is the acid, which by default makes this the base. To figure out the conjugate acid and conjugate base, we can look at the reaction going backwards. In this case, the Cl was Cl-, and it becomes HCl, so it is accepting a proton, which means this is the conjugate base. And by default, this is the conjugate acid. And the conjugate acid is the one that is going to be donating a proton. H3O+ donates its proton to Cl-, which makes it H2O. We can use pKa's, which is the negative log of Ka, to measure the acid strength. pKa is the negative log of Ka. This measures acid strength. So if you have a smaller pKa, this indicates a stronger acid. The pKa of water is 15.74. This is a value you should definitely become familiar with. So what a Ka or pKa tells us is how far the reaction proceeds in an acid-base reaction. So a Ka is a concentration of acid times base over Ha, which is also the same as H3O+ times OH- over water. And you can see these values here. So for water, it is 1.8 times 10 to the negative 16th. The pKa equals 15.74. The Ka is a measure of how much of the acid will dissociate into hydronium ion and conjugate base. We can look at the relative strengths of different common acids. Ethanol is a weaker acid. Water, as we know, is a weak acid. And if we get down to HCl, that is a very strong acid. If you notice the pKa's of ethanol, 16. -7 is a very strong acid for HCl. And the conjugate base of each of these you can observe here as well. So weaker acid, stronger acid, weaker base over here, stronger base. So one thing that you might observe is a stronger acid means that it will have a weaker conjugate base. So this is HCl, which is a strong acid, but Cl- is a weak base. You will not need to memorize these pKa's, except for water. So if we want to rank these substances in order of increasing acidity, we want to remember that high pKa equals weak acid. So the value with the highest will be the least acidic, and the one with the lowest value will be the most acidic. So if I put this in order, acetone is a pKa of 19. The pentane dione has a pKa of 9. This is 9.9, 4.76. The weakest one will be acetone. The strongest is 4.76. Then 9.9, the phenol is next. And then the pentane dione. So we can just move these from highest pKa to lowest pKa. This is least acidic. This is most acidic. We can use pKa's to predict how the reaction is going to proceed. If we have acetic acid with hydroxide ion, acetate ion plus water, we can use the pKa values that are related to their logarithms to determine the equilibrium constant. So we can use this to determine whether or not a reaction will happen, which side the equilibrium lies on. So if you have a higher pKa, that means it's harder to remove a proton. Proton being H+. So we just saw on the last slide the pKa of acetic acid was around 4.8. Water is 15.74. So when you're trying to predict the acid-base reactions, compare acids. Because we have the pKa values to support that. The value with the higher pKa is water, which has 15.74, which means it's going to be harder to remove this proton. If it's hard to remove this proton, that means that most of the product is going to be on this side because the acetate ion will not be able to take that proton off to go to this side. So this side of the equilibrium is favored. So the equilibrium favors the high pKa because the high pKa means that we can't remove this proton very well. If we can't take the proton off, then it can't go in the opposite direction. Organic acids come in different shapes and sizes. They're generally characterized by the presence of polarized hydrogen atoms. They can lose a proton from an OH. So these would be organic acids. Methanol can lose this H, so can acetic acid. It can also lose a proton from a CH. And this is usually next to a CO bond. So this one here would be an H next to a C double bond O. So these qualify as organic acids. The pKa of each of these, methanol is 15.54. 4.76, and this is 19.3. An organic base has an atom with a lone pair of electrons that can bond to H+. Nitrogen-containing compounds are the most common organic bases. Oxygen-containing compounds can react as bases when with a strong acid or as acids with strong bases. So methylamine here has this lone pair. It's a nitrogen that's going to act as a base. The oxygen here can act as a base as well, and so can the oxygen lone pair of acetone. So Lewis acids are different from Bronsted acids. Lewis acids are electron pair acceptors. So we're dealing with electrons here and not protons. And the Lewis base is an electron pair donor. Bronsted acids are not Lewis acids because they can't accept an electron directly. Only a proton would be a Lewis acid. And there's no scale of strengths as in that Bronsted definition of a pKa. Lewis bases can donate their electrons. Lewis acids can accept electrons. If we look at boron trifluoride, which is a Lewis acid, this is the electron space fill of this here. The boron can accept electron lone pairs from the oxygen here. So this would be the Lewis base. This is the Lewis acid. This is the acid-base complex. So Lewis bases can accept protons as well as Lewis acids. Most oxygen and nitrogen compounds are Lewis bases because they have lone pairs of electrons. Some acids can act as both depending on the reaction. So we can see here some examples of Lewis bases. Alcohols, ethers, aldehydes, these all have the electron lone pairs. The sulfur as well, nitrogens, and then we can see phosphorus or this phosphate compound because of the oxygen lone pairs. So if we look at this, which of these are likely to act as Lewis bases? We saw on the last slide, oxygen, nitrogens are very good at acting as Lewis bases because of the lone pairs. So this would be, and this would be, these two are going to be considered Lewis acids. So if we look at an application of organic chemistry, all foods are organic. Organic in the dietary industry or in the food industry is commonly thought to mean it has no synthetic chemicals or pesticides or is less dangerous or risky. This is not always a good definition of that because organic food farmers do use chemicals and pesticides. They might be natural ones, but they do use some to some extent. And the other thing is that the FDA does not really regulate what is considered organic or not. If there's a compound that is organic in the whole food item, that can be considered organic. So they don't really police that. If you're making cereal and one ingredient on there was organic, they could slap the organic label on there. So pesticides are used for weeds. They use herbicides for that, for insects. They use insecticides, and they use fungicides for molds and fungi. If you use no pesticides whatsoever, and you may have noticed this if you've ever had a garden over the summer, there's a significant drop in crop production, which would increase your food costs if you were a farmer. So it's not really ideal for an organic food farmer to not use any pesticides at all, because they have to deal with weeds, insects, or mold. So one of the things that is used is atrazine, which is used on crops. There's 100 million pounds used each year to kill weeds in sorghum, corn, and sugarcane. And there's trace amounts of this that persist in the environment. Exposure can pose health risks to humans and animals, but there's no alternative but to use this. The EPA will not ban this pesticide due to resulting dramatic increase in food costs. Currently, the benefits outweigh the risks. So what I mean by that, they use atrazine on food crops, and if you use them, your crops of sorghum will increase by 13 bushels, increases 7 bushels of corn per acre. By not using these things, your food costs and your farming costs are a lot more. If we look at the risk versus the benefit analysis, strychnine is a nasty poison that has a lethal dose of 0.005 grams per kilogram, which means that in a group of 100 people, 50 people would die at this dosage level. For arsenic trioxide, it would be 0.015, and you can see the different things here. Ethyl alcohol, which is in our alcoholic beverages, is 10.6. So they tested the atrazine in animals at a much higher level than you would see at normal exposure. The results were converted to an LD50 value, which is at 100 people, 50 die. So the results were converted to an LD50 value, which came out to be 1 to 4 grams per kilogram. That was lethal for 50% of the testing done in animals. This has no information on long-term exposure risks. So there was a small amount of, the LD50 is low, especially considering that aspirin also has a similar LD50. So because of the benefits of the atrazine outweigh the risk of health, the FDA will continue to allow the use of atrazine on crops.